Howdy everyone, I'm Michael Perch. I'm a professor at the University of Texas at Austin, and I just did a short lecture on Kriging for an undergraduate class here, and I promised to record it and dedicate it to them, to the Geostatistics, Data Analytics and Geostatistics course here in the Hildebrand Department of Petroleum and Geosystems Engineering. This is dedicated to you. Let's talk about Kriging. Fundamentally, this is our problem, is that we need to make estimates in space. Now, the problem we have is that our data is often sparsely sampled. Example here, we have Y and X. We're looking down in space. This could be an area of interest that represents maybe a reservoir, maybe an ore body. So we have locations 1, 2, and 3 that we've sampled. Those are places at which we have data. And now what we need to do is we need to map or estimate in between those available data. For instance, at this one unknown location right here. So the question is, how do we go ahead and make that prediction given that we know the values at these 3 locations? It'd be a very natural thing to do would be to go ahead and say, let's just take a linear combination of those 3 values, ignore this part right here, 3 values with some type of weights. So lambda are data weights, z, u, alpha are the values at these locations, porosity at this location, this location, this location. And if we take the sum of the weights multiplied by the values, that would give us an estimation model. Now what's very interesting is if you look at that equation, you ignore what's in the red box, I hope you can see that if we're going to say, let's assign more weight here, less weight here, or let's say we say all of the data should get low weights or all the data should get high weights, I hope you can immediately see that that would create a bias. That if we have high weights for all the data, we would estimate with a larger value. And if we have low weights for all of the data, we would estimate with a lower value. So we need to complete our spatial estimate with an unbiasedness constraint. An unbiasedness constraint simply says 1 minus the sum of the weights will go towards the global mean of z. And if we do that now, you could imagine if we use very low weights for all of the data, we'll estimate the global mean. That's unbiased. And if we have large weights and say the sum of the weights is equal to 1, then we won't even use the mean at all. So 1 minus sum of the weights will control, it's basically like a weight on the global mean. Okay, so this is our fundamental prediction that we're going to make, and it's a linear weighting to make an estimate. Okay, so now, how are you going to go ahead and assign those weights? Well, it's pretty logical. If you look through here, all of the data are almost the same distance away from the unknown location. So closeness seems like a good criteria we could use. And from that criteria, we'd say 1, 2, and 3, very similar distances. In fact, maybe 3 is a little bit further away if you look carefully. And you might say that 3 gets a little bit less weight. But now we have to be concerned about something else. What about data points number 1 and 2? They're closer to each other. They're somewhat redundant. In fact, you could do the thought experiment. Imagine if you would go ahead and move these 2 points towards each other. At some point, they'll almost be on top of each other, and they'll be completely redundant with each other. They'll tell you the same information. Finally, what other piece of information would you want to use? You'd want to use the concept of the variogram, because the variogram tells us for a given separation, distance, and direction, what is the degree of similarity, the covariance, or dissimilarity, the variogram value. So we want to use that. So how are we going to go ahead and incorporate all of these aspects of closeness, redundancy, and the variogram and make spatial estimates? Well, we can go ahead and take our linear estimator and we can pose it as an estimation variance. What are we saying? We're saying if y star is our estimate and we're using the sum of these weights multiplied by the values. Now I've removed that unbiasedness constraint because I'm going to assume either we have a zero mean or we're working with a trend and the residual has a zero mean. And so we're going to assume that we can remove that component right there for this calculation. Now we take that y star, our estimate, minus the true value at a location u is a location vector, and we can go ahead and calculate the square of that and the expected value because we're working over all of the locations we want to make estimates. So, not a bad thing, we want to go ahead and calculate this estimation variance. Now it's very interesting, and this is why I say it seems a little magical, because many students see this the first time and they say, but you don't know the true values where you're estimating. How can you calculate this? What's fascinating is if you take this quadratic and you expand it, and that's what's being done right here, and you can break it apart because that's the nice thing about expectation. It's a linear operator. You can distribute it into each one of the components after you do that. If you make some substitutions, including the y star, the estimate, substituted every time you see y star, and you further expand and simplify it, what you'll see immediately is you get these terms right here. Expected value of ui, yuj, expected value yu, yui. Now, given the fact that the means are assumed to be 0, I hope you can see that this is the very definition of covariance. In other words, we can replace these expectations. This one becomes the covariance between 2 points in space, 2 data points between them, and this becomes the covariance between the unknown location u and the data points. And this, the covariance at 0 lag distance, is simply the variance of the problem, the data, or known as the SIL when you did variogram modeling. So we can calculate the estimation variance without knowing the true value, and all we need to know is the locations of the data and the variogram model. And from the variogram model, we can calculate the covariances. Okay, so that's all we need. Now, that doesn't get us to our estimation problem. We want to go ahead and calculate the weights, those spatial data weights, such that we minimize that Kriging that estimation variance. And so we can go ahead and take that previous equation, do the partial differential with regard to the data weights. And as we do that, and there's some steps involved in it, but because we're doing optimization, we can set this equal to 0, move this to the opposite side, and what we end up with is this equation right here. It's a linear system of equations that we can work with. In fact, we'll have n equations, n unknowns, n weights, and n equations that we can work with. So now we're ready to define Kriging. It's a spatial estimation method that relies on linear weighting. And I showed you that equation. It accounts for spatial continuity, the variogram. You saw all those covariances. It accounts for data closeness, and it accounts for redundancy. But let's, don't worry, we'll dive into more details and we'll show you this in multiple ways. What we can also say is that the linear Kriging estimates are unbiased, and the weights are assigned such that they minimize the estimation variance. And we did that. We did a minimization by doing the partial derivative and setting it equal to 0. But let's go ahead once again. We'll look at that system of equations. We can expand it out right here for our problem with 3 data and 1 unknown location. This is what our system of equations becomes. Now, for those of you who prefer matrix notation, and I do, it's quite nice and clean to look at, we can take this system of equations and we can simply write it right down here. And so now what we have is we have a left-hand side, which is the covariances between data point 1 and 1, data point 2 and 1 right here, data point 3 and 1 right here, and all of the combinatorials. So we got all the pairs of covariances between the data. This is perfectly capturing in a pairwise manner the redundancy between the data. Then what we also have on the right-hand side is we have the covariances between the unknown location. That u with no index is the unknown location, the estimate location, and we have the covariance between 1 and unknown, 2 and unknown, 3 and unknown right there. So this system of equations encapsulates closeness and redundancy and the variogram model. Now remember, covariances can be calculated just by taking the SIL minus the variogram values, so don't worry, if you have variogram model, you're ready to go. What are some of the interesting properties of Kriging? Number 1, we can solve this system of equations, invert the left-hand side, multiply it by the right-hand side, and calculate the weights as long as the Kriging system left-hand side, this covariance matrix for redundancy, is positive definite. And this is guaranteed if you use nested permissible variogram models. And you probably remember that, the nugget, spherical, exponential, Gaussian, and there's more. Those variogram structures, if you use them and you use them properly, you know all of the rules. You can vary the ranges, but the contributions must be the same in all directions for each of the nested structures and so forth, right? Okay. We can go ahead and we know this is going to be solvable. And that's part of the reason we did all that variogram modeling. Kriging estimator is unbiased. The expected value of your estimate minus the truth should be equal to 0. There'll be error, but you'll be centered on 0. And that's due to this unbiasedness constraint that we included at the very beginning. Of course, if we use a trend model, which is what we're assuming with 0 mean and of the residual, it simplifies to this. This cancels out, but it's implied that we have an unbiasedness constraint. It's a minimum error variance estimator. In fact, I have an Excel spreadsheet you can check out on my Excel numerical methods GitHub repository, where you can actually go ahead and play with it. You could change the weights yourself. And what I promise you is you cannot beat Kriging. You will not be able to pick weights that will get a smaller error variance or Kriging variance. It's a best linear unbiased estimator, and that's because it's linear, yes. Best because it minimizes the Kriging variance, and it's unbiased, and it's an estimator. It's an exact interpolator, so it has exactitude. And what that means is that the data locations, here's an example of a one-dimensional section in space X, lithium grades part per million. The black line, I grant you superhuman power that you can see the truth. You don't have the truth, but that's what it is. But you only have these data points here, and here, 3 drill hole locations. And if you look at those locations and you do Kriging, you get a model like this, the red line, and that model does pass through the data at the data locations. You will estimate the values of the data at the data locations. It is your new best friend. Kriging is going to not only give you the best linear and unbiased estimate, but it's also going to tell you how bad that estimate is, or how good. That's fine, it might be very good. The Kriging variance, shown right here, can actually calculate the uncertainty or how accurate that estimate is. It is a measurement of variance, so it means that you take the square root of the Kriging variance, you get the Kriging standard deviation. And so, rules you might have in your head as far as like plus or minus 3 standard deviations or 2 standard deviations and so forth. You could assume a Gaussian distribution, build an uncertainty model. This is a map of the Kriging estimates, simple Kriging, right here. If you look really carefully at it, there's some really interesting things, is that you can see the data locations are the circles, and then what you can do is you can come over here and you can actually produce a map of the Kriging variance, because every time you get an estimate, you get the estimation variance, the Kriging variance. And can you see the values where it's 0? The black dots right there, there, and there are exactly where you have data locations. If the data lines up exactly at the cell centroid, sometimes they don't line up perfectly, you'll see little black dots. And away from it, the Kriging variance is increasing. In other words, your estimates are getting worse away from the data. Okay, so Kriging variance. The Kriging variance can be calculated before getting the sample. Isn't that crazy? I think that's really interesting. If you look at this equation, this is the variance. These are the weights from the Kriging system. This is the covariance between the unknown location and the data locations. Do you see any z's or y's in this equation? There's no actual values. In other words, this Kriging variance is independent of the actual data values, the estimates. The only thing that comes in, of course, will be the CIL or the variance. But in other words, if I was to go ahead and ask you a question, what would happen to the Kriging variance map if I drilled a new value right there? I drilled some more data right there. You could update this map without actually knowing the value. Pre-drill, you could tell us how much you'll reduce the uncertainty. That's interesting. It means it's a homoscedastic uncertainty model. It's not dependent on the mean value or the estimate. The variance and the mean are independent of each other. Kriging takes into account closeness. I've said this, the redundancy, structural continuity, in other words, the variogram. Smoothing effect of Kriging can also be forecasted. And when we get into simulation, we'll talk a little bit about smoothing effect. I think you saw that right here. It looks very smooth versus the truth. That's a topic for another day when we talk about simulation. There's a couple more things we can talk about right here. Outside the range of the data, simple Kriging weights will all be equal to 0, and the best estimate is the mean. Okay, and that makes sense, that you'll have no weight on the data. 1 minus the sum of the weights is equal to 1. All of the weight goes to the mean. Screen data will sometimes have negative weights. This allows Kriging to extrapolate. If we think about the data being zero-centered, you have negative values, positive values. This is in space right here. If you have a negative value with a negative weight, you get a positive result. Positive value of a positive weight, positive result, and depending on the magnitude of these, you could actually, for this estimate at this unknown location, you could extrapolate outside of the range. Negative weights allow you to extrapolate. It was here, data point here, and then when you estimate here, make it even higher. You see that? So you're extrapolating. Strings of data will have an artifact sometimes known as the string effect. What does that mean? If you have a lot of data on a string, but you have good horizontal spatial continuity, you'd imagine that you should have greater weight right here where you're closer. Closeness is important, right? But you'll have that distribution, but if you keep having more and more data of higher and higher resolution, like samples very close to each other, at some point redundancy will start to win. In other words, these data points on the very ends will seem so much less redundant than the data right here in the middle that eventually you can end up with a distribution like this where all the weight goes to the data on the ends. This is called the string effect. In many software programs, they avoid this effect, like for oil and gas, where we have strings of data along wells, by only taking a couple of the nearest data from every well when you make an estimate. So they have methods, they call it octant search, where they just say, I'll just take certain number of data from different directions, or they'll have maximum number of data per well. They'll have something like that. Okay, so let's go ahead. I want to demonstrate some of these concepts in Kriging right now. So what I have for you is a couple of interactivities to walk through. The first interactivity is right here, and you can load this up. In fact, this is called Interactive Simple Kriging Behavior, and it's available on my GitHub account if you want to check it out. Let me go ahead, open up my GitHub account here, my interactive repository called Data Science Interactive Python, and if you go down here, you're going to see Interactive Simple Kriging and Simple Kriging Behavior. Those are the two workflows I'm going to look at. Now, if you haven't gone to GitHub before, check out GitHub. There's tons of great stuff that people share. This is my GitHub account. I have many things here, including 2 of my ebooks, course, my Python package. There's tons of educational content here to help you out. I even have one of my repositories is a inventory with links to all of the things that I share. Okay, let's go ahead and open up this dashboard. We're going to talk a little bit about different aspects of the Kriging system. When you open up the Simple Kriging Behavior, Interactive Simple Kriging Behavior, IPYNB, which is a Jupyter notebook, you should get something that looks like this. Let's go ahead and we'll skip through this, some of the explanation, but we'll get down and run it until we get to the very first dashboard right about here. So in this dashboard, what we're going to do, we're going to switch it to exponential. To be honest, I think I haven't configured it for spherical. It didn't seem to be working, but I have it set up. I can see it looks like an exponential result. We'll work with that. What this is going to do is it's going to allow us to explore closeness, i.e., what happens as we change the distance of a data point away from the unknown location. Let's look at this plot. We've got unknown location. Variogram range. You can change all the variogram parameters. If you don't believe me, look really carefully. You should see that starting to become elongated, and I'll bring it back down. I want to keep it isotropic for this example to keep it simple. We have the blue data point right here, data point 1. We have the red data point 2 right there, and the red data point will stay in the same location. The blue data point, we can move it. Okay, so let's go ahead and move that data point right on top of the unknown location. Do you see what happens? The weight on blue is 1, the weight on red is 0. The sum of the weights is equal to 1. 1 minus the sum of the weights is equal to 0. There's no weight given to the mean. What is our estimate right now? We're estimating with whatever value is at the blue data point. That's our estimate because we have exactitude. We're estimating at a location where we have data. Okay, we expect exactitude from Kriging, and that's what's demonstrating for us right now. Now, if we take and we start moving the blue point further away from the unknown location, can you see what's happening? The weight on 2 is increasing, or red is increasing. The weight on blue is dropping pretty fast, actually. And we'll reach a point, if we keep going, where the weight on blue is equal to weight on red. Do you see what's happened? We're equidistant. That's 200 meters. 200 meters this way, and there's no redundancy issues. They're equally close. They get equal weights. And we can keep moving. If we keep moving across, this is interesting. You'd think at the range, which is shown right here, that we should get the 0 weight. Let's try it. 0.12, 0.08, 0.05, and now we have 0.03. Now this is very interesting, and you might be concerned with why do we have any remaining weight when we're beyond the range. And the main reason is this. The parametric model for exponential, that positive definite structure, is an asymptotic function. It reaches the sill asymptotically, which means it never gets there. And so we have to call the range at a convenient level of the sill. And so what we do is we say 95%, 5% remaining to reach the sill, and we call that the range. And you can see that right there. In fact, what's kind of very convenient, you can see 0.05, 0.03, and at some point it'll basically disappear. It'll shrink to a small enough value we don't really see the weight anymore. 0.26, the remaining weight 0.74 going towards the mean. At this point, we're mostly estimating with the mean. Okay, I hope that was useful. That demonstrates the impact of closeness. And then what I did is I generated another one of these dashboards, and this demonstrates the concept of redundancy. So what we're going to do is we're going to take these 2 data points right here, and we're going to move them very close to each other. So we can move them all the way until they're right on top of each other. And at this point, they have a weight of 0.28 each. Now, if you don't believe me, look at this plot right here. This blue and red line dashed are the weights for both blue and red points. And you'll notice they're always the same as each other because our problem is very symmetric, right? But the weight on green is 0.57. Now, if you look within some type of rounding, when we're estimating at this unknown location right here, you can see that if you take the weight of blue plus the weight of red, it's about equal to the weight of green. In other words, they're completely redundant with each other, and they're just sharing the weight. And they're both equal to 1 green right there. Okay, so now what we can do is we can go ahead and we start separating them. Watch what happens. 0.28, 0.29, 0.3. Now, if you look really carefully, you should also see that these weights are jumping up and the weights on green are dropping. Green is becoming more redundant with red and blue as they move around and get closer to it. And they're getting less redundant with each other. Now, what angle subtended do we expect to see these all have equal weights? Well, that's that point right there. That's 120 degrees. What's special about 120 degrees if we're talking about these data points? 120 degrees, they're all equidistant from each other. And so what happens? They all get equal weights. Now you can keep going around. Redundancy is kind of interesting. They're becoming very non-redundant with each other, so they're still increasing in their weight. And do you see what's happening right now? Green is losing its weight because it seems very redundant with regard to the red and the blue at this point. And if we keep going, we'll reach a point where green, in fact, starts to get negative values. Do you remember what I talked about? Negative weights indicates the screening effect. We're starting to see the ability of Kriging to be able to extrapolate outside the range of the data with these negative weights. And this is happening because of the fact that we have a situation in which these are closer to each other. This is highly redundant. And this one is seeming like it's basically being blocked by those other two data. All right, so that was the demonstration of the behavior Kriging for closeness and redundancy. You could have done a bunch of things changing the variogram model. That would have been interesting. Look at that. You could put a whole bunch of geometric anisotropy, make it kind of complicated like that. You could rotate it. So all of these examples could be conducted where you dramatically change. Wow. Okay, that's pretty crazy. So there's a lot of things you can do to explore and understand what's going on with Kriging as you use very specific, very different variogram models. Okay, let's go to this one here. This is the interactive simple Kriging. Let's play with this a bit. I want to invite you to try some things out. And so this is a nice example because it shows us not quite, and ignore some of these warnings. These are just, there's been an update where it's a little more sensitive about equations within my captions. I'm not going to fix that right now. I'll get to that later. Let me zoom in. What we have here is a very flexible dashboard. The problem is that you have blue, green, red data at those locations of the x's. You have the weights. You have their actual values. So now we can actually see the estimates. You also have the sum of this is the unknown location right here. This is the variogram range shown right here, so you can get a sense of data are within range or not. You have the estimate at the unknown location. Now, right now, if you look really carefully, it's 38 for an estimate at this point for porosity, so 38% porosity. And the mean was provided underneath the hood as 38 overall. And so now the weight on the mean is 1, the weight on all of the data are zeros. And so we're just estimating with the mean. Okay, so let's just try a couple of things out. I think this will be kind of fun to play with. We could take the red data point and move it a little bit higher up. Let's demonstrate the screening effect by taking the blue data point and putting it right about here. Now it's like a screenshot in hockey. We got to move this data point in front, blocking that other data point. So let's go ahead and we can move it in front. Oh, I forgot one thing. We got to make sure we have enough spatial continuity because otherwise nothing has any relationships. Okay, so let's go ahead and we'll create a massive amount of spatial continuity so everything is nicely correlated with the unknown location. And if you look really carefully, you'll see data point, the blue, has got a really strong weight, and the red point now has a negative weight. And that negative weight is being caused by screening. It's allowing this machine to be able to extrapolate in the prediction. Yeah, we're demonstrating it here because we have 4, 3, 43, 25, and our estimate is actually outside the range of the data because of these negative weights is 20.7. So it saw like a trend. This is high, this is lower, this is even lower. So it did that. Okay, let's try a couple more things out I think would be useful. We can go ahead and we can move that back down a bit. Move it over. If we do that, we get back to kind of a nice behavior. We could play around with trying different anisotropy ratios. Right here, we could drop this down right about there. If you look at the variogram, you can see the minor direction, the major direction, and these are all the directions inferred in between using geometric anisotropy model, the equation of an ellipse effectively. And you can start doing some fun things like this. You take and rotate this. You can see the direction of major direction continuity is 0, 0. So in the north-south direction, and you can see we get the most spatial continuity with red. Now we go ahead and we just rotate that like that. You can see it's starting to lose spatial continuity. Red has almost got no weight at all. Now red has no weight, but blue is starting to get some weight. Blue starts to get some weights. 0.52, blue is getting a lot of weight. Green is starting to get some weight. So as we rotate around, you can see kind of how that's happening with the weighting. The other thing you can do, of course, is what we did before with the redundancy. You can move blue kind of right beside red. That's kind of fun. And then move it over. And see what happens when you start to move it over towards red. Oh, I put it right on top. I jumped a little bit. Sorry about that. Okay, Let me go just a bit over. So we put them kind of close to each other. And we move it forward a bit. It's being screened at this point. That's why it's getting 0 weight. Let's bring it down. What's that, 901? Let's put them exactly at the same place. 901 on Y. Now that's very interesting because of the fact that the red is exactly lined up with the spatial continuity direction and it has so much better correlation. It appears to be it's getting all of the weight from this other one. So let's go ahead and move that over just a little bit. Okay, now they're starting to share a little bit of weight. So we can see some really neat behaviors here. We can even grab this and move it even closer, closer, and they start to share even more weight together. So you get a sense of how their weights are being shared. Now, if you look over here, you'll see that this is taking the Kriging estimate, the Kriging variance, shown right here, and it's assuming a Gaussian distribution. It's building the CDF. This is an uncertainty model you could use at work, in fact, which is really, really cool. So let's go ahead and try other things. How would we maximize uncertainty? We could cut that. We could increase the nugget effect. So if you increase the nugget effect, more and more nugget effect, if you take it all the way up to 100% nugget effect, there's no spatial continuity with anything. And what you can see is 0 weight, 0 weight, 0 weight, and the sum of the weights is equal to 0, all the weights on the mean. In fact, what's interesting is the Kriging variance at this unknown location just becomes the cell because you have no data, you have no information. Okay, there's many other things you can do to play around with Kriging. I like this display because you can really visualize it, but go ahead, try to break Kriging. Try to do all kinds of neat things with the varogram and the orientation of the positions of the data and see what happens. I hope that was helpful. I'm Michael Perch. I'm a professor at the University of Texas at Austin, where I teach and conduct research on data analytics, geostatistics, and machine learning. All right, everyone, take care.